Hi, we're Moing 787 and we're doing our project on the wing flaps. I'm Sarah Kashanchi.
I'm Mohammed Sharif.
I'm Gurkaran Kocher.
And I'm Nicholas Caselli.
The Boeing 787 Dreamliner aileron. How it works. Now, the aileron is used to generate rolling motion for an aircraft. For example, if the aircraft wants to turn to the left, the right aileron is deployed. This deployed aileron creates a high pressure zone and the disturbed airflow pushed against it. Now, this disturbed air push creates a thrust, and this in turn creates a torque about the fuselage. Now, since our center of gravity is kept along the fuselage, the plane is able to rotate about the axis of the fuselage, and that's how it turns. How the mechanism works. Now, here we are analyzing the aileron flaps on the Boeing or Moing 787. As we can see, this is the mechanism for the aileron, and the above diagram describes the two toggle positions which enables the aileron to lower to a 43 degrees of angle. And we go on to how the wing flaps work. Now, we estimated that the time to open and close is individually 1.7 seconds. And how we got to this value is that we assumed that the ailerons both take the same time to open and close. And with that assumption, we found a video on YouTube that clearly describes how the ailerons are deployed. And we measured the time by using a stopwatch and recording the time 4 times and taking the average of the 4 to obtain our value. And once we obtained that value, we multiplied it by 2 since to account for opening and closing.
So to talk about the selected lengths of links, which are an estimation, we researched on multiple different sources for the specific dimensions of an airplane. One website in particular gave us appropriate dimensions. The total length of the airplane is approximately 56.7 meters and the wingspan is approximately 60 meters. These dimensions are important and provide us with a scale to work with. However, it is not what we need. The aileron is just one component on the wing and has approximate dimensions of 13.5 meters by 1.35 meters, which is seen above. Now to talk about the length of the aileron to analyze each link. Analyzing this mechanism, 4 components were made. They were independently analyzed as 4 links as seen above. Point D and point A are both grounded and do not undergo any motion. They have angular velocity, however no linear velocity. Points A to B have an approximate length of 0.08 meters. Points B to C have a length of 0.23 meters. Points C to D have a length of 0.173 meters. Points C to E have a length of approximately 0.68 meters. Points D to E have an approximate length of 0.63 meters. And now talking about our designs. The designs are seen above. An extruded version along with a view from the side is seen. The actual aileron is a component in the wing flap and is extruded as seen with the image on the right side. The mechanism in motion as seen by the observer when sitting in the aircraft is the extruded component, which is seen in the right image.
So to determine the mobility of our mechanism, we use the mobility equation, taking into account the number of links, or N, the number of joints, or J, and the overall sum of the joints and their degree of freedom. There are only 4 links, with 1 being the ground. There are also 4 joints, and since each component of this mechanism has only 1 degree of freedom, the summation of degrees of freedom for each joint is 4 as well. Overall, using the mobility equation, our mechanism has a mobility of 1, meaning that it would only need 1 motor to operate. So next we analyze the mechanism to determine its Grashof criteria. We use the 4 links mentioned in the mobility slide previously with the link connecting the grounds, shown in red. This is the longest link and this is fixed, while the other links have the ability to move. The shortest link is shown in blue, link 2, having a length of 0.08 meters. The longest link, as mentioned previously as the ground, has a length of 0.321 meters. The other 2 remaining links, light blue and green, have values of 0.23 and 0.173 meters, respectively. Completing the Grashof criteria analysis, we can see that the left sum has a value of 0.401, demonstrating our mechanism as a Grashof Type 1 or crank rocker. The blue link 2 has the ability to crank 360 degrees, but for the purpose of our project, the crank can only function within a range of 124 degrees, allowing the aileron to decline 43 degrees as required. This is a quick animation showing the side view of the system. Note that the crank can only move in the designated 124-degree range. Consequently, the aileron will move in a 43-degree range motion. This is a simple illustration of the trajectory for the tip of the aileron within its 43-degree range of motion. Here we can see an isometric rendering of the aileron to demonstrate its three-dimensional movement.
As for the velocity and acceleration analysis, we looked at two separate components, the cranking part as well as the aileron tip. In this slide, we analyzed the crank's angular velocity and acceleration. The graphs shown on the left that were generated in SOLIDWORKS represent the absolute magnitude of both, and we can see that from 0 to 124 degrees relative movement, both angular velocity and acceleration behave in a sinusoidal fashion, with a 90-degree phase shift between the two. On the right, we have a velocity diagram of the entire system. It should be noted that this diagram was created under the assumption that the crank would operate under uniform angular velocity, whereas the graphs on the left assume oscillation between the minimum and maximum points. It was found that the maximum velocity of the crank was approximately 11 centimeters per second. In this slide, the tip of the aileron was analyzed. Similar to the crank, the aileron operates in a sinusoidal fashion with slight deviation due to its oblong shape. The graph on the left demonstrates this. On the right, we have the velocity diagram of the system, including the tip of the aileron this time. We found that when the linear velocity of the crank was 11 centimeters a second, the linear velocity of the aileron tip was approximately 13.5 centimeters per second. Something we don't get to do much in this class is hands-on work, so we decided to assemble our system in order to gain a more tactile understanding. We quickly created this model directly from our CAD files through laser cutting, and here is a quick stop-motion animation showing the link movement. This concludes our presentation. Thank you for listening, and please refer to the report if you have any more questions.